Internet of Things, and digital twin applications in the health sector. The Internet of Things, IoT, is an enabler of smarter environments in multiple sectors. Together with digital twin technologies, it is demonstrating an evolving potential to not only optimize existing services, but also create new ones. The purpose of this presentation is to provide an introductory overview of the applications of these concepts and technologies in the health sector. Biodigital convergence, a 20-year-old concept. In the context of biodigital convergence, the phrase convergent technologies refers to the synergistic combination of four major NBIC, nano, bio, info, cogno, provinces of science and technology, each of which is currently progressing at a rapid rate. A. Nanoscience and nanotechnology. B. Biotechnology and biomedicine, including genetic engineering. C. Information technology, including advanced computing and communications. And D. Cognitive science, including cognitive neuroscience. Here is your biodigital convergence, and as you can see, they have different working groups. They have everything covered, from engineering to biology, nanotechnology, and informatics. Here is your genomics, your biotechnologies, synthetic biology, your biosensors, bioinformatics, computational biology, cybernetics, systems engineering, genetic engineering, stem cells, and here's your CRISPR-Cas9. Here we have working groups 3, 4, 5, and 6, which take care of the medicine, health, human augmentation, environmental engineering, and smart farming. What do we have here? Biomanufacturing, bioelectronics, biomedical devices, organ and human body on a chip, artificial organ, cyborg, biobots, bionic implants, biohacking, biomaterial, environmental monitoring, geoengineering, smart cities, GMO, cellular agriculture, and molecular farming. This is all part of the biodigital convergence. Here, in human augmentation, you have good health and well-being. Embodied computing has zero hunger. In bioelectronics, we have clean water and sanitation. In environmental monitoring, we have life below water and life on land, as well as the clean water and sanitation. Geoengineering and smart cities have climate action and sustainable cities and communities. Smart farming, GMO, and cellular agriculture also have zero hunger. Bioprocessing and molecular farming is responsible for consumption and production, and biomanufacturing has industry, innovation, and infrastructure. Definition of IoT. Internet of Things infrastructure of interconnected entities, people systems, and information resources, together with services, which processes and reacts to information from the physical and virtual world. The IoT is a system concept that uses many technologies that are standardized by other JTC1 entities and SDOs, ranging from networking and digital twin to cloud computing, big data, and AI. IoT systems are software and data intensive as well as network centric. They can be quite complex, ranging from simple architecture to multi-tier distributed computing, cyber-physical systems. IoT systems are key enablers of quote-unquote smart everything. Here are your sensors. On the left side, we have biosensors. Sensor 3.3.29 that uses specific biochemical reactions mediated by isolated enzymes, immunosystems, tissues, organelles, or whole cells to detect chemical compounds, usually by electrical, thermal, or optical signals. On the right side, you have quantum sensors. So they have sensors for everything. Graphene-based sensors and health monitoring. On the left, we have invasive applications. Your nervous system, ECOG, neural stimulation. Your cardiovascular system, your ECG and blood glucose. Your digestive system, gastrointestinal diagnosis. Your locomotor system, EMG and muscle stimulation. On the right side, we have non-invasive applications. Your biophysical, electrophysiological, EEG, EOG, ECG, and EMG. Kinematic, pulse, heart rates, respiration, phonation, facial expressions, blood pressure, joints movements, gesture, muscle movements, and thermometer, your body temperature. These graphene-based sensors also have non-invasive environmental applications like light, gases, and heavy metals. They have biochemical applications like volatile gases, electrolyte, metabolite, bacteria, drug, dopamine, tumor markers, and others. Let's keep scrolling. Smart everything, everywhere. Here is your smart society, smart payments, smart healthcare, smart buildings, smart transportation, smart energy, and smart territory improvement. What can you do with IoT in the healthcare industry? Remote patient monitoring, telehealth, assisted living, hospital asset management, improved drug management, hand hygiene compliance, chronic disease management, and behavior modification. Yes, the Internet of Things in the healthcare industry can modify your behavior. Here is your body sensor network, and it's taking your EEG, your EMG, your blood pressure, your ECG, your motion, and your thermometer. And it's pulling all of that data to a local process unit, which, as I've said before, could be a wireless device like your cell phone, computer, or any smart device you have in your home or within your vicinity. Or it could even be the augmented air molecules that are around you. And it's sending that data out to the internet so that your end user, like your local physician, the hospital, or your family, but only if your family has the clearance to access this data. It also stores all your body sensor network information on a body sensor network care server. And this is what your satellites are actually for. They are pointing down at you, collecting data from inside of you, from inside of your bone and tissue. Here is your smart healthcare. So again, they are pulling all of this information out of you and your body area network, and they're sending it to a healthcare server, which your physician or caregiver has access to, as well as emergency services or medical researchers. See your heart rate and respiratory rate, your motion, and it's all pulling that data to the internet for the end users. I don't think the majority of the population realizes that this has already been done, implemented, and deployed. This is how telehealth works. This is how your remote healthcare works. Convergence IT/OT. IT/OT convergence is the integration of information technology, IT systems used for data-centric computing, with operational technology, OT systems used to monitor events, processes, and devices, and make adjustments in enterprise and industrial operations. The evolution of IT/OT convergence. And as you can see, they've been at this since the 1970s. In the 2000s, they had integrated architecture. In the 2010s, they had 5-layer architecture. And 2020 plus, they have different modules with seamless integration. Industrial, Internet of Things, building blocks. A hospital is an industrial facility. As I said before, they use this technology in the hospitals. The Internet of Medical Things is a network of medical devices, hardware infrastructure, and software applications used to connect healthcare information technology, sometimes referred to as the IoT in healthcare. IoMT allows wireless and remote devices to securely communicate to allow rapid and flexible analysis of medical data. Here you have application, data management, network, and data collection. Smarter Healthcare has real-time monitoring data with big analytics and machine learning. And this lovely image here shows all your smart sensors. Moving on to digital twins. Definition of digital twin. A digital twin is a digital representation of a target entity with data connections that enable convergence between the physical and digital states at an appropriate rate of synchronization. Note 1 to entry. Digital twin has some or all of the capabilities of connection, integration, analysis, simulation, visualization, optimization, collaboration, etc. Note 2 to entry. Digital twin can provide an integrated view throughout the life cycle of the target entity. Digital twin technologies. We have physical, which has sensing technology, measurement technology, material technology, dynamics technology, process technology, and hydromechatronics. We have data, which has fusion technology, visualization technology, processing technology, transmission technology, collection technology, storage technology, and knowledge technology. We have services, which also has knowledge technology, software and platform technology, architecture technology, and algorithm technology. Then we have connections, which has internet technology, interfaces technology, communication technology, interaction technology, collaboration technology, and security technology. And we have the model, which has modeling technology, simulation technology, visualization technology, model VV&A technology, and model evolution. Five data V's of digital twins. Volume. The volume of data aggregated in a digital twin varies considerably depending on the mirrored physical entity, but quite a few physical entities are bound to generate a significant amount of data. Velocity. The shadowing of a physical entity again varies considerably, but here again can have a significant quote-unquote change rate. Variety. A digital twin may aggregate different streams of data, like the actual modeling of the entity, static, the operation data, dynamic, the context data, static and dynamic. And in addition, it can harvest data from the other interacting or connected digital twins. Veracity. Internal and external functionalities can authenticate data and ensure their veracity. Value. Digital twins are a way to create value in the digital transformation. Human digital twin. Ecosystem for digital twins in healthcare. And on the left, you can see some companies that are involved in Europe. The Internet of Things and environmental monitoring. We have monitoring networks, data anywhere, anytime, smart sensors, IP data loggers, digital water, cloud-based telemetry, and smart cities. Biosensors. On the left, we have your bioreceptor, which could be nucleic acids, proteins, or whole cells. You have the transducer, which is electrical, optical, or thermistor. And you have the amplifier, which is signal amplification. They have 2D, 3D, and 4D printed microfluidics. Autonomous fluidic actuation and handling. This is your biosensors. You have the sample. You have the transducer, which is electrochemical, optical, piezoelectric, and thermometric. And where do we use biosensors? We use biosensors in environmental monitoring, soil quality monitoring, food quality monitoring, pathogen discovery, drug discovery, toxin detection, water monitoring, and disease detection. Let's keep scrolling down. Human augmentation technologies. Phase 1. Recovering. Repairing the existing impaired human physiological functions. Most assistive technologies in this phase, for example, rehabilitation exoskeleton, focuses on the rehabilitation scenarios in hospitals and at home. Phase 2. Replicating, substituting human functions and organs. Power augmentation exoskeletons, rehabilitation exoskeletons excluded, and artificial organs are common examples at Phase 2. External devices that supplement the daily life living. For example, smartwatches and VR glasses are also considered as typical use cases. So your smartwatch, your VR sets are already Phase 2 of the human augmentation. And Phase 3, enhancing, outperforming human capabilities. Applications aiming at exceeding human abilities are performed using emerging technologies, from biomechanical engineering to genetic engineering. And down here you can see your global human augmentation market. As an augmented human, we'll have enhanced intelligence, enhanced sensing, disease-free bodies, sports optimization, digital hardware enhancements, enhanced strength, increased attractiveness, optimized diet, extreme aging, digital biometrics, and ubiquitous and continual monitoring. Cyber physical systems, CPS, comprise interacting digital, analog, physical, and human components, engineered for function through integrated physics and logic. These systems will provide the foundation of our critical infrastructure, form the basis of emerging and future smart services, and improve our quality of life in many areas. And here we have the brain-machine interface, BMI, concept.